just go ahead and diving into this. So as background, whenever I give a talk about roofs and unvented roofs, I like to tell people like, what should I build if I want to do something durable, high performance? Vented roof, done. Call it, stop talking. Basically, the roof sheathing is completely exposed to that attic space that you can walk around into. Moisture just, if you have any leaks, air leaks from the interior coming up, that could condense. It's all getting whisked away by the ventilation up in that attic space. And you can send somebody up there to walk around, look for water leaks, and find them and fix them. That being said, air leaks solving air leaks at the ceiling is absolutely critical to make these types of assemblies work. Whether you're doing, drywall knit together with spray foam, a layer of, zip sheathing with tape joints, whatever you have, service cavity, basically the air tightness of that attic floor is the critical thing to make them work. So why would we be going into hard mode and build living space into the roof and require insulation up at the roof line? Well, obviously like we're doing here, the conditioned space goes up into the roof space, so we need to have insulation up at that line. And most of, you walk around New England, so many of the houses, that's just the normal way that they're built. Vented cathedral assemblies, same kind of thing. Vented specifically, those are, we're talking about sheathing, vent chute, insulation. Those are often real dogs in terms of thermal performance. You have a limited space for insulation, but even worse, you only have one line to solve the air leakage problem, and a lot of the time it just goes south and they are giant sieves. Also, in terms of venting roofs, you have all these complicated roof lines, dormers, valleys, etc. You just can't vent stuff like that. There are also cases where you have a ceiling plane that's Swiss cheese, speakers, ducts, everything. As well as HVAC in vented attics. Basically that's the dumbest spot ever to put any type of mechanical system, somewhere that's screaming hot in the summer, freezing cold in winter. Why would you ever put ductwork with R6 insulation around there? That basically talks about this whole concept. So the resulting solution we've come up when people say, we're not sparing any square footage for any mechanical closet is like, fine, we'll move the insulation line up to the roof line. You can keep your ductwork up in the attic, but at least it's not screaming hot at 120 degrees all summer long. So there are also folks who are espousing doing, roofs with dense pack insulation, dense pack cellulose in the rafter bay, no ventilation associated with that. I cannot say I recommend that. There are folks who do that as a retrofit. They are risky. They do have failures due to moisture reasons, which we'll dive into in here. More importantly, it is not actually, if you look at the code, section R806.5, that's not a code compliant assembly. So I don't understand why you're saying that you can build that if it's an obvious code violation. And the way that they fail is what's referred to as ridge rot. So what ends up happening is the majority of the roof is fine, but up at the very ridge is where the moisture kind of concentrates over time, and you end up with a pattern like that where the ridge beam, the sheathing up at the ridge, that's the stuff that takes the brunt of the damage. We'll get into that in a bit, skip over that. So why are unvented roofs with fibrous insulation like cellulose or dense pack fiberglass, why is that risky? Nobody's saying like, oh my gosh, unvented walls, that's a risky thing. Like, no, it's, so what's the flippin' difference? So let's first talk about what's the actual mechanism that's causing this problem. So the big thing that kills them is interior source to air leakage, wintertime, warm humid air, gets through imperfections, travels through this air porous insulation, hits the cold roof sheathing, condenses, or even worse, frosts up. That's where the damage occurs. Vapor also, part of the problem a little bit, but very small in comparison to air leakage. Big thing, the vast majority of roofs, what are we putting on top of it? Peel and stick, felt paper, asphalt shingles, right? All of those materials are pretty much zero perms. You've basically put a perfect vapor barrier on the wrong side, the cold side of that assembly. So, we tell people not to do that on walls, but that's exactly what we're doing on roofs. So that's another risk factor. Another factor is night sky radiation. So that's an infrared shot showing house with the walls compared to the roof. So, so what you're seeing there is that the roof surface is way colder than the wall surface. Both of them are insulated layers. What's going on is something that is facing the sky is going to experience this thing called night sky radiation, where heat wants to jump off of the roof surface to that cold night sky, and that gets way colder than the walls, which face kind of the street, the yard, that kind of thing. So colder surface, greater risk of condensation. So that's another risk factor that's going on. Stack effect, warm air rising, pumping air into that assembly ain't gonna help. So the result of that is ridge rot, where the air kind of percolates up, gets to the ridge, and that's where the worst damage happens. Risk become lower if you have better air tightness, basically less of that air getting through, hitting that sheathing. Dense pack, a really good dense pack, that also controls how much air filters through that. If the sun comes out more often, that'll dry out your roof that much more. But on the flip side, the north side of the roof or the side of the roof that's under your solar panels, hey, that doesn't get as much sun. A giant driver of whether these roofs survive or die is what's the interior relative humidity. If you're driving this at like 20 to 30% relative humidity all winter long, you can get away with a lot, frankly. That's probably why more of them work than not. If you have a client, though, who is insisting like, oh, I need 50% relative humidity all winter long for health reasons, like, good for your health, gonna kill your building, is the takeaway from that. And reducing the vapor permeance as well as an air barrier, that'll help as well. What is a basic code compliant assembly? Just to walk through what the code actually says. So closed cell spray foam shot against the underside of the sheathing, totally common, works all the time. It's right out of the book. I know folks are trying to avoid closed cell spray foam, high carbon materials, all that, but this does work. You can also do a hybrid, a flash and blow of certain ratios of closed cell plus fibrous insulation, or you can flip that around and do rigid insulation on the top side of your roof sheathing with insulation, fluffy insulation inside your rafter bays. That works as well. But this, just so you know, this is a heck of a complicated roof to build. You're building your structural sheathing, then your rigid insulation, walking around on that, another layer of sheathing, finding your screws all the way through that, and building your actual roof on top of it. Yeah. Oh yeah, absolutely. I work, I work with, the top end of builders are doing this, but there are so many cases where you bring this assembly like this and they'll say, what do you want me to build? So that's the conflict that you'll have to face. So the thing is, it would be delightful if you could build these kind of assemblies without spray foam or rigid foam on the top side. And there are all these retrofit, options for retrofit cases as well. So moving on from that to some of the previous research. So it's, we've done multiple test huts all around various places. This was a little garage test roof we built in Chicago, climate zone 5. We only had it for one winter. We cranked up the humidity to 50% just to make everything fail as much as possible. Takeaway is they all pretty much failed. They grew mold on the underside. The cellulose one was probably the least bad of the unvented roofs. But the vented roof actually was that was the vented roof with that air chute over the insulation. That actually worked out fine in terms of moisture. It's just a dog in terms of energy performance and air leakage. We also did some work with this diffusion vent concept in both Orlando and Houston. So what is a diffusion vent? Remember, I was talking before about ridge rot. That moisture kind of works its way up to the ridge. That's where it ends up concentrating, and you have all your problems up there. why not take advantage of that by, if the moisture is going to collect there, instead of a ridge that's just open with, mesh or, the airspace, we put a vapor open but air closed, water closed membrane. Think, Tyvek, but even more vapor open. Over that, knit it into all the control layers, and basically let the moisture release there where it's called concentrated. The takeaway is, yeah, that worked well enough in the warm enough climate zones that it's part of the building code nowadays for climate zones 1 through 3. This just kind of shows that assembly going together. That brown membrane is the super open membrane we use at the ridge diffusion vent. Tape down just to make it airtight, and then throw a regular ridge vent over that. Shows it with a tile roof. Yeah, so this just talks a little bit more about ridge rot. Yeah, I'm gonna skip this because we have not a huge amount of time. Well, let's go ahead and talk about this part. So, I don't know, have you guys been dealing with open cell spray foam roofs with humidity problems up in an attic? I'm not sure how many people do open cell up here, but this is actually a thing. Basically your client, your homeowner goes up into the attic with the open cell and says like, why is it 70% humidity up here and why are the ducts dripping water? It's like, oh, that's not good. So what's going on is it's the design of an open cell spray foam roof is a little bit worrying and has problems because the open cell foam allows moisture to bounce in and out of the sheathing and it ends up concentrating over time. So we refer to this as ping pong water. So basically, the sun comes out. We have black shingles, insulated roof deck. That roof sheathing is getting screaming hot. 150-ish, over 150-ish. Screaming hot. Basically, all of that moisture is getting blasted out of that roof sheathing into the attic. So, bone dry during the day. Then come nighttime, roof sheathing cools off, and then all of a sudden, all that moisture in the attic just sucks right back in through it, through the open cell. With closed cell, this is not a problem. Open cell, it is a problem. So basically, this moisture is ping-ponging in and out of the roof sheathing, concentrating more and more over time. That's how we end up with that problem. This is very similar to like a chemical engineering way to concentrate gases. So it's this solar-powered machine that concentrates moisture on you. Yeah, skip that. So let's talk a little bit about this Westford test hub. This is from maybe 2020-ish or so. So the takeaway is, we did all of those previous experiments and said like, man, there are a lot of cool techniques and materials out nowadays. We got, all these variable perm, vapor retarders that are now out there that allow drawing downward. We got this diffusion vent idea. Maybe we can revisit this whole risky dense pack cellulose roof and maybe we can get it to work. So what we did is Joe Stiebrick built a test hut in his backyard, and we have pairs of north-south test bays, and each of them is one insulation system. We had a whole bunch of different variables from which vapor retarder we chose, variable perm versus fixed perm, the diffusion vent at the ridge, diffusion vent or no diffusion vent, fiberglass versus cellulose. You'll see there are more fiberglass roofs than cellulose roofs. It's the cellulose sponsors gave us more money, that's why. And also, we did a comparison to a control of just a regular, bog standard, code compliant, closed cell spray foam roof. How does that one behave in comparison? We ran it for 3 different winters. First one was normal interior conditions, like 20-30% relative humidity, pretty dry, normal-ish. Second winter was we cranked up the humidity to 50%. Third winter, we intentionally injected air leakage into the rafter bays to see the effect of that. By the way, hey Andy. So this just shows some of the construction. We had guard bays in between our test bays, basically preventing cross communication. Here are like the different, you know, cellulose and fiberglass materials, the various vapor retarders, the detailing of the vapor retarders, stapled, glued, you know, gasketed, everything. Just shows an overview shot looking around there, showing the various test bays. And basically the whole setup ready to go. And after the interior vapor control layers. This shows how we built those diffusion vents, basically just top of the rafter bay, chopped out the top of it, stuck down our brown membrane to allow that drying, taped it down, and just threw a regular ridge vent over that to hopefully allow that escape of moisture. So, I'm trying to figure out the best way to summarize this without putting you all to sleep. There's literally a 120-page report that you can download and enough, you know, graphs to make your eyeballs bleed. But hopefully here are the top takeaways. You know, these non-diffusion vent roofs, the one that just had peel and stick over the ridge, yeah, those accumulated moisture up at the roof, at the ridge, exactly like you would expect, you know, and there actually were moisture problems up there. Having the diffusion vent helped a lot, and we calculated whether we should get mold up there or not, and they said it was safe. One interesting bit is there was a lot of settling of insulation. So this shows the fiberglass roof. You know, you could stick your hand down into the top of that and, you know, there's, you know, big void up there. What was even scarier to me is the cellulose roof. I'm like sticking my tape measure way down in at the ridge, and we peeled that back a bit further, and this one, that shocked me, is, you know, that's basically like a 2-inch cavity, and the whole thing just kind of shrank like that. And I could run my tape measure basically down the whole length of that. That, you know, that's kind of scary town to me. And this was a insulator that was selected by the insulation manufacturer to do a better than average job. It's like, yikes. Yeah.
Any indication of why that happened? Is that like increased moisture causing weight density?
Yeah, that's my... Yeah, that's an interesting thing that I've seen once is an experiment where they just took cellulose in a container and they cycled it high, low humidity over a bunch of cycles. And that actually made it noticeably settle within the test stud bay that they had. And it's kind of like basically the cellulose particles are doing, you know, basically expanding and contracting with the moisture change, and basically it's settling down like the way that you shake the cereal box to get the prize to kind of rise up. You know, same thing.
Year one, this is before the saturation.
Oh no, this did get somewhat damp, so you know, not bone dry by any means. Yeah, we left the roofs as is with that void setup just because, you know, we try to repack this roof, we're going to wreck a couple of instruments is the takeaway. I'll skip this inward drive thing. So year 2, we basically ran it through at 50% relative humidity. Yeah, these were pushing way higher towards failure. You know, the moisture content in a lot of the roofs up towards the ridge getting 20, 30%, which is, you know, I don't know if you guys speak moisture content. The way to think about it is under 20%, you're fine. 20 to 25, like, yeah, that's starting to get risky. 30%, yeah, we're getting into, you know, oatmeal territory. So basically, that's risky town. The mold index calculations said we were fine, and then we took it apart. Surprise, we grew mold. Thanks, guys. And another interesting bit is, you know, like we're looking at all these data points going like, oh, 90 plus humidity, you know, what moisture content? This is all pretty risky. At the same time, the closed cell spray foam roof is getting subjected to the exact same conditions. It's going like, I'm fine, I don't care. Basically all the instrumentation saying like completely well below any type of risk threshold. You know, say what you want about not wanting to use closed cell, but it does do the job of keeping interior moisture away from the roof sheathing. It does do that job. So after that winter, we repacked it, basically replaced some instruments that had failed. Basically, the installers came in, ran their hoses, just dense packed the living snot out of everything they could. Okay.
The closed cell?
No, the closed cell was just left as is because nothing had really changed there. So also during the summer between those 2 years, we did some disassembly and that stuff does not actually look great, so we pulled off the vapor retarder. This is the netting underneath the fiberglass, and I don't know if you can quite see that brown diaper stain from back there, but basically that's a water stain that accumulated at the ridge, ran down, hit some type of a joint, dripped into the fiberglass. Yeah, that might or might not be a callback, not sure. Yeah, I don't know if you can quite see the mold that's on the cellulose bays, but little dots of mold. And I was shocked because I always think of cellulose as being way safer than fiberglass. It's got the borates, it's got all that good stuff, but data is data. I saw what I saw, and that is the closer shot of the settling pattern. Yeah, so takeaways from that, interesting point is that, we added this air injection with the same 50% relative humidity. We saw high moisture contents where we injected the air, but the moisture levels up at the ridge in some of these remaining roofs were substantially drier than the previous year when we had that bad dense pack job falling down. So yeah, the packing matters. That suppresses airflow. And that matches up with all the cellulose guys who say the only way these things work is if you dense pack the living snot out of them and make sure of it. It's yep, that matches up with what I'm seeing. Yeah, and where we injected air, yeah, we spiked the relative humidity. Yeah, probably not enough time to talk about this. All these miscellaneous measurements, yeah, the data.
What was happening at the soffit?
So what we did is, the word, use the term chainsaw retrofit or not, or
yes.
Yeah, okay. Basically, so the line of air, yeah. Yeah, so the line of air control is right here at the wall. There is no overhang built into the structure, so basically there's a perfectly airtight connection wall to roof. And then in this case, we actually built out with 4 inches of mineral fiber, and the carpenters built this kind of a box truss for the overhang, and that's bolted back through into the structure through the continuous insulation. Water control is on the top of that. That is the ultimate way to get amazing airtightness with this kind of a structure. This building, by the way, was so airtight that I turned on the 50 CFM exhaust fan, and I think I depressurized the building 50, 60 pascals or something like that. It's crap, my exhaust fan is actually affecting my experiment because air is coming in through my assemblies instead of going out. It was that big of an effect. And this is just like a bathroom wall fan. Yeah, I'm not going to talk about data. Way too much to talk about, but basically I'm going to go to the takeaways of what did we end up recommending. Yeah, here we go. So the takeaway to me is that, these kind of unvented fibrous insulation dense pack assemblies, they can work. Dense pack cellulose, dense pack fiberglass. The things that are really key is ensure complete packing of the insulation in those cavities, and you're still vulnerable to small air leaks. We did find mold, which is still kind of a bit scary, and it all concentrates up at the ridge. Takeaway from this is it is difficult for us to say this should be allowed in the code, just because the way I always think of it is you put something in the building code, it's going to be built by the worst possible trades with the worst possible materials with the worst possible quality control. They're going to try to build an unvented roof assembly with cheap, low-density fiberglass bats and go, air barrier testing, blower door, what's that? That's what you're likely to end up if it's just part of the code. What would be great is if this was allowed as a retrofit for failing assemblies. In case of disaster, break glass and use this technique, but there is nowhere in the building code that says you can use this in an emergency or something. So if somebody's asking me, we want to build foam-free, unvented roof assemblies in a safe manner, and the answer is yeah, you can totally do that. It's all within the building code. It's all off the shelf. So all you can do is, do this, except not with foam. Use mineral fiber, use Styco, or any of the wood fibers whenever Timber HP gets themselves online. Do that in the correct ratio of the cavity insulation to the exterior, and you're off to the races. That totally works. Another fantastic performer, but it's a lot more work. I don't know if you know the guys up in Maine who are doing passive house modular stuff, but this is, Chris Corson's the guy who does that. This is his roof assembly, and I'm got to say, that is beautiful. So the layers here, this is the actual structure, the structural rafters, dense pack between that, structural sheathing, and your first layer of membrane. You're dried in at that point. You've got the unvented roof that's not code compliant yet. So then what he does is he basically builds, I don't know if you passive house guys, refer to it as the Klingenberg wall or not, or it's basically these TJI outriggers on top of the rafters, entire thing filled with cellulose. So you've basically put a layer of exterior insulation outboard of your non-compliant assembly. So at this point, it meets code. Then you put a layer of Mento, totally vapor open membrane. Beautiful. This entire thing can dry out. Cross-strap cavity, put your roof on top of that. That is a primo roof. That is amazing. That can dry out like crazy. Is this complicated? Yeah, it's complicated. That's why they build it in a factory on the ground.
How do they fasten that outer structure to the...
The TJIs, or the TJIs, just there are screws driven through into the rafters. Because they're in the factory, they know exactly where their framing is. So that's the easy part of the problem.
Easier than driving screws through 4, 6, 8 inches of foam.
Yep.
Down to your rafters.
We're hoping to find it.
Probably in some ways easier.
But thermally not as perfect.
Not as perfect. No, absolutely true. Yeah.
What is the thermal bridging of the OSB in that scenario?
Yeah, so this is a tidbit that I heard from John Straub, who's my grad school advisor from way back, is that even though TJIs have a really narrow web, OSB is so much denser than dimensional lumber that the thermal bridging is in the same ballpark. It's I did not realize that, but that's a fair argument. I've not confirmed this. I've not run a therm model to confirm, but that's what he said. But the takeaway with that combination, that's a pretty darn good roof.
What's the ratio of the top foam to the fluff inside?
Yeah, so the ratio of those two, the outsolation versus insulation, is really critical. So the key is you need to meet a minimum of a certain amount of exterior insulation per climate zone. Here in Massachusetts, climate zone 5, we're talking 40% minimum outside. And go up to zone 6, Maine, etc. I think that bumps to 50%. Yeah.
How I've heard on the internet.
Yeah.
Building Science Corporation helped develop those.
Yes.
How conservative are they?
Yes, they definitely are. So full background. Joe Stiebrick.
Back to what you said earlier,
Yeah.
the worst builder is going to build this.
Yeah.
We have to.
Exactly. Yeah. So Joe Stiebrick, BSE's founder, was the author of R806.5, that part of the building code that talks about unvented roofs, and all that stuff with air permeable, air impermeable insulation. That comes from him. So those ratios are basically a bunch of woofy simulations that Chris Schumacher and John Straub ran to basically kind of bound the problem. It's like, yeah, this is kind of the range of humidities we might see and the resulting risks. And that's the number plus a safety factor. This is definitely not a case of 40% is the code requirement. You go to 39%, your roof is screwed. Of course not. It's a matter of like, how cold is it this winter? Is it the north side or the south side? Do we have trees over it? Is there a solar panel over it? Is it a dark roof or a light roof? What's your humidity inside? All of those things are way more important than 39.99, So just wrapping up this, oh yeah, go ahead. Yeah.
Percentage matter compared to the wall in terms of those percentages of outsolation versus install?
So wall versus roofs. If you look at the code requirements for walls, it's less stringent for walls. I think climate zone 5, we're talking 30% outside rather than 40%. That goes back to, way back in my slide deck where I talked about, we have a vapor barrier on a roof. We don't on the outside of a roof. We don't have that on a wall. Roofs face the sky and have night sky radiation. All of those things make those differences. So, so I usually wrap this up talking about, if you're really dead set on doing one of these unvented fiberglass cellulose assemblies, I call it against medical advice. You are legally allowed to check yourself out of the hospital while you're still bleeding. It doesn't mean it's a good idea, but you can do it. So, if you're going to do that, how would I tell people to keep themselves safer? Keep the interior relative humidity low for the life of the building. That's the real big challenge. There's lots of stuff that'll work at 20%. It turns to snot at 50%. Air tightness of the interior air vapor control layer. You guys are all high performance. You do blower door tests. You know what that's all about. Using a variable perm vapor retarder. If you dig into my report, you'll see that there are spots where the fixed perm trapped moisture up inside the roof assembly, but the variable perm vapor retarders, hey, stuff got to dry out. It works as expected, like it says on the tin. Use as big of a diffusion port as you can fit with as vapor open of a material as possible. Dense pack without voids. And if you're doing a light colored roof or shading it with a solar panel, yep, risk is going back up again. This is an entire experiment that Brendan and I would be happy to talk about over beers afterwards. But I think the priority is let's talk about the roofs that are going up here, right? Cool. So any question, feel free to shoot questions as we're, come on.
The closed cell in the rafter bays, do we have to encapsulate the rafters to prevent moisture from going through the 2x12 rafters? Should that be encased as well?
I would not bother encasing the rafters for moisture reasons. Basically vapor diffusion through a solid stick of lumber, pretty minimal. That being said, if you have the space and you want to improve thermal performance, yeah, putting insulation at your thermal.
And the entire roof deck has got ice and water shield on it, and those rafters are drawing moisture in. You're just allowing them to dry out to the inside because they can't get out?
Yeah, so there's the whole discussion of drying with all of these spray foam roof assemblies. And I definitely agree, peel and stick on the top side of your roof sheathing, close cell on the underside. There's not much drying going on. Is it completely zero? There's some inward drying to some degree. But, does this mean that these roofs fail? Pretty much no. They're pretty much a known commodity. Where you have a bad flashing detail, yep, you rot out your roof, your sheathing over there, and you go up and fix it. You fix the flashing detail, you put the roof back together, right? So given that, I would not bother trying to do all these special measures to help the sticks dry, is my takeaway. Sorry, here, holding up your hand for a while.
No.
Yeah.
No, thank you. That's very interesting. I was wondering, for the closed cell inboard of the roof sheathing,
Yeah.
how many inches are sufficient for the like class 1 perm rating. It's like 2.5 gets you to 0.8, but so like what's the optimal amount, I guess, of closed cell foam to not necessarily for the R value, but for the vapor?
Yeah, to me, the vapor problem is a pretty low priority because the first priority is air, because air transported moisture moves a boatload more than vapor diffusion through the solid material. Closed cell spray foam has that down cold once you get past 1/2 inch to 1 inch. The next piece is the whole ratio requirement of 40%, 60% that I was talking about with that kind of hybrid of closed cell plus fibrous. So that's probably going to drive the bus way more than anything to do with perms is my thought. And all of this is predicated on like, are you running a normal-ish humidity building versus like, if you're doing a swimming pool, that's a completely different animal, for instance, or or a museum where they are definitely going to condition up to 50% relative humidity all winter long. That's a different problem for sure. Yeah.
Thank you.
Josh, please.
So 2 real quick things that correlated. One of them, does any of this change with trusses versus rafters? And the other one is there's been a lot of talk about gaps from the foam drying inward and creating pockets and pathways to the sheathing, especially on in non-exterior insulation assembly.
Yeah. So first question on trusses versus framed rafters. My thought is that's just a geometry and hanging stuff problem more than anything else. With a rafter, you could probably do something like that hybrid of closed cell and bat and find some way to strap your bats in place. With the truss, you're kind of screwed. So the least bad thing I could come up with, closed cell and spray open cell, just so you're not hanging, strapping all over the place. In terms of the foam splitting problem, that's actually definitely a big deal. So, I don't know how many of you have seen spray foam splitting. It is typically an application problem where basically the foam has a level of dimensional instability. Basically, you heat it up, cool it down, heat it up, cool it down. It tries to stay stuck to the rafters, and it can't, and it just either splits in two or it splits off the rafters. And you are absolutely correct that if this splits all the way through, guess what? We've opened a pathway from the interior air up to the cold roof sheathing. Yeah, you could have a stripe of moisture damage, although I'm not sure quite how common that is, but it absolutely is possible. There are all these tips and tricks that you can do to try to improve the quality of your spray foam installation. Look up JLC. Henri Fennell and Mason Knowles have both written fantastic articles on that. But takeaway is, what's coming out of the gun is super important. The ratio of the two chemicals that are coming out of the bins. The temperature of the substrate, the moisture content of the substrate. Doing a little fillet bead at the corners just to kind of get stuff stuck together. There are all these little bits and pieces, but and unfortunately the spray foam industry has to some degree devolved to any dude with a truck can be a spray foam installer. So that's kind of the reality that we're stuck with now.
Corbett Lunsford just posted a video this week on his YouTube channel about checklists that you can go through. I didn't actually watch it. Did you watch it?
Yeah.
Checklists you can go through to hopefully get the best result you can.
It's not just for spray foam, it's for foundations, framing. It's like a 45-minute video on different checklists that you can find, and one's on spray foam.
Oh, okay.
You can find Henry Fennell's checklist. He did a summer. No, he did. Oh, did he do a BSc beer? But I know he's been at the summer camp.
For sure, yeah. Henri Fennell, for those who don't know him, he is the rock star of spray foam. He's up in northern Vermont. He spent a bunch of years running his own spray foam company, doing really innovative stuff, and nowadays he just consults on spray foam. Half of his jobs are like, hey, we have another spray foam failure and we're suing people. It's like, okay, guess I'll do that. Yes?
I'm really mystified by the dense pack jobs and how much.
Yeah.
That's really interesting.
Yeah.
Were those dense packed to 4 pounds per?
Yeah, unfortunately, we did not get to measure it on the front end on that. I did measure it after we repacked the roof, and it was high 3s, if I remember correctly. So that
Still a separation even with that high 3s.
no, sorry. So there was the first two years that we let it run with that settling. Then there was the last year where we shoved in the hose and repacked it. And I got to rip apart the roof myself and take out bins and weigh them to measure the density. And the one and remember that third year, that actually worked way better than the previous year. So that's the one that said, yep, density matters a whole lot.
Sorry, I missed that picture then. Did it separate at all?
Yeah, that one did not settle. Yeah, so that was high 3s and did not settle.
So it's important because
Yeah.
when there's that separation, better than me, that's the worst case scenario because then the sheathing becomes cold.
Well, not only it's cold, but you also have an express path for any moisture that's getting through your assembly. Whoosh, just goes right up to the sheathing, right up to the ridge of the sheathing. Nothing's stopping it.
Did you repack that from the top?
From the inside. Yeah, basically they, cut slits in the netting up on the, standing on baker staging and just shove the tubes down and just pack, more pack, that kind of thing.
Have you ever dense packed with half-inch CDX as opposed to netting to get a really tight pack?
I've never actually done a blowing machine, so I would, how strong your netting is, whether it pops out, I can totally imagine that is huge for sure. But yeah.
Matt, what are some things we can do to have a good result with our dense pack? Wood fiber, obviously.
Wood fiber and cellulose. I come from a cellulose background, but I'm with Timber HP, just as everybody knows. I think density and distribution is key, especially in larger assemblies. I mean, we're regularly seeing people speccing out 18-inch, 20-inch, 24-inch. I was on a 28-inch thick dense pack project with installers that had never dense packed before, and these are things where if you want to get the right density, it has to be well distributed, not just half of it sticking a hose in somewhere. I mean, people have to be methodical and care. I think using a stiff needle, like a stiff aluminum tube, helps you get that high density rather than a smaller Tiger Flex or loose tube, particularly in these like really large cavities. It's hard. You have to have an installer that cares.
Yeah.
That wants to do a good job. And it's tricky. And as we get into these bigger assemblies and unvented assemblies, it becomes more important because the risk is greater, right?
Yep, for sure.
Do better than I can.
So do we want to shift gear to these assemblies? Also, if please feel free to get up, get another slice of pizza, use the bathroom, whatever you want. This is open forum. We're just going to kind of hang out and. Okay. So does somebody else want to introduce these assemblies, or should I just go ahead and take the wheel and walk through the whole thing?
Go ahead.
Okay. So these guys gave me 4 different building assemblies to play with and talk about here. So this is what I refer to as the top ventilated assembly, coming from the top. Standing seam metal, some type of an entangled mesh. Is it still sitting over there, giving us maybe a 3/8 inch airspace? Some type of a super vapor open roof underlayment to allow drawing from the sheathing outward. CDX, the existing 2x12s that are up there. Looks like adding Styco strips kind of as a thermal break, just to make it less not continuous framing all the way through. Intello as an air vapor control layer, 2x4 strapping as a service cavity, and gypsum board on the inside. So the key thing that bothers me about this assembly is that, to me, this is not a vented assembly, a code compliant vented assembly. To me, if you think about what a normal code vented assembly is, it's interior, air barrier, insulation, airspace. Just think about like the walkable attic where you're walking around, underside of the sheathing, and then your roof. So basically that airspace, the vented airspace, is protecting the sheathing from that moisture. Basically, that's a spot where the moisture can whisk away. This one, we only put that airspace on the top side of the sheathing. So therefore, the sheathing is no longer protected by the vented airspace, is how I put it. So to me, I don't think that's a vented assembly. This is pretty much the same dense pack assembly that we're talking about in the previous research. Do we have drawing through the CDX and the Vapro Shield? Yeah, absolutely. Is that safe enough to work? Maybe. I'd still, want to put a vapor diffusion port at the ridge of that, just because moisture is going to concentrate its way up at that ridge, and just because that's where it's going to end up concentrating. So the two different assemblies we're talking about here are. Oh, thank you. A code-compliant vented assembly where the chute is below the sheathing, or this thing where we put an airspace above the sheathing. So this to me is, like you build a code-accepted unvented roof, closed cell, rigid foam, whatever, and then you have this chute on top of that. That is great for ice damming because the snow will never melt. You're not losing heat through it to melt the snow. And it's incredible for durability. You've basically built two roofs, but this is not a code vented roof is the takeaway.
Meaning the vent space is on the underside.
Yeah, that's my thought on the design. Any pushback, counter thoughts, Andy, or?
Can you hear me all right?
Yeah, I can hear you.
Okay, great. No, I think that was one of our takeaways from this as well, is that we have the ventilation, but it's above. We were also curious, so we started this assembly out with burring, essentially, and cross burring above the sheathing. So I don't know if the change in the depth of the airspace above changes anything really, down from like the entangled mesh, which I assume is like a 3/8 inch or so, up to giving it more room to really ventilate. But the fact that it's all above the sheathing, I think is still consistent with what you're talking about.
Yeah, so for those who didn't hear, one of the secondary questions in his discussion was using just a 3/8 inch mesh versus full 1.5 inch air cavity. I would bet there is a boatload more ventilation airflow through that full unobstructed cavity. Don't ask me to quantify, but if somebody told me between a factor of 10 to a factor of 100, yeah, I'd believe that. If somebody has data otherwise, I'd be happy to listen to that. But just to kind of talk through what could be similar to this and kind of work, this is a fine home building assembly that was shown. So it's a similar dense pack assembly, dense pack between the rafter bays. And then what I believe he did is there's, WRB stapled to the 2x12s. So basically it's this totally vapor open membrane on top of those insulated rafter bays, little 2x2s, 2x4s, and that creates that air cavity. And at that point, it's, that's the same as a code compliant cathedral roof, except that's, a piece of house wrap instead of a crappy foam, Owens Corning chute, right? That's, that works. That's meets all codes and is incredibly durable. Is it a pain in the butt to build where the guys are trying to crawl up the roof on strapping while they're and trying not to step through that membrane? Absolutely. But in terms of the hygrothermal behavior, yeah, that works.
Did you design that roof, Kohta?
No, I had nothing to do with this. I just was reading Fine Home Building and I'm like, oh, that's a nice one. Yeah. Oh yeah, totally. Yeah.
Portland, Oregon, and if you're interested in something like that, you'd be more than happy to talk to you about that assembly, I'm sure.
Yeah, and DuPont actually tried to do something like this commercially a decade and a half ago. Basically what they did is they had this membrane that draped across the rafters, and they had these U-shaped plastic clips that basically clip on top of the rafters to basically create an airspace like this. Basically, they tried to market it, it went nowhere, and it got disappeared down the memory hole. So moving on to roof assembly number 2. So this is basically empty rafter bays and airtight vapor control membrane on the top side. Continuous insulation, big sandwich of insulation, ventilated airspace, batten, cross batten, and then roofing material, shingles, metal roof, membrane, etc. It's like, yeah, this is a fantastic performer. It pushes out your roof a fair amount. But if you're somebody who was asking me for an incredibly durable roof, yeah, this would be up there. Joe Stiebrick wrote this article called The Perfect Wall. It's about the assembly that he considers the ultimate for durability, where you have structure, a membrane, and your insulation all outboard of that, and you just kind of hang your cladding as the pretty. And that's basically what this is. The reason why it's so durable is your structure, all of those rafters or your walls or your CMU block, that's going to run at room temperature for the rest of time. So think about, how do we preserve things in a museum? We keep it out of the rain, we keep it at a constant temperature, we keep it at a constant humidity. That's what we're doing with the structure with this. So this is basically the same assembly that Joe built on his barn. Yeah. He put a lot of foam on his barn. And actually, the ridiculous thing is this is the remodeling of his barn, because he originally did it with EPS foam and ants got into it, and he's like, screw it, I'm gonna rip it all apart and do it all over again. Seriously, Joe? Yes. What am I gonna do, buy another Porsche? It's like, okay, Joe, your money. So that's basically the assembly. Basically, it looks like a barn from the inside. You see all of the timber structure, all of the inside of the barn board. He put down a layer of tar paper just to black out the joints between them. Layer of plywood just for additional shear and racking. Put peel and stick over the entire structure. That's the first picture. Then piled up the foam and put the remaining exterior sheathing and all those layers on the outside of that. Is this a lot to build? Yeah, it's a lot to build, for sure. One more warning on this assembly that somebody pointed out to me that kind of blindsided me when he first said it is, you're putting strapping and cross-strapping over rigid insulation. What's your ground snow load in this climate zone? So average that PSF, concentrate it into your furring strips, and what does that equal relative to the compressive strength of your foam? It's like, ooh, crap, I didn't think of that. So one more thing to put on the list. This one is basically a pretty close to bog standard vented cathedral assembly. Airspace underneath the sheathing, spacers to allow the ventilation channel, cavity insulation, smart vapor retarder. Perfectly code compliant, totally works. That, it's a relatively forgiving design in terms of any moisture that gets through. You have this great relief valve to send moisture out of your assembly. Yeah, the problem is that you've only got one spot to make an air barrier at your, variable perm, Intello layer, so you better get that one right. This one is beautiful in that it has a service cavity down here, so all of those holes are just gonna be in the pretty layer, the one that doesn't matter. The other thing to realize though is, vented cathedral roof assemblies totally work with simple geometries, hunk like that. What you do when you have a project like that, and you can ventilate the middle part, the middle wing of the house. Everything else has dormers, skylights, all sorts of crap. That ventilated assembly just is not gonna work. Doing it over here, where we have a nice simple barn, totally works, although you have a limited amount of space, so basically you're building down or you're building up to make that work. Also, like I said, cathedral roofs leak air like crazy. This is just, standard construction. I was doing a blower door test middle of the summer, so the hot air leakage will show up as warm spots in the infrared. I am depressurizing, so I'm sucking in hot air from outside, and you'll see that, screaming amounts of hot air coming in through the ridge vent, concentrates where we have stuff like can lights or other obstructions like that, it's a mess. It's, you know, it's not good. You know, and if somebody told me how would the, you know, what's an awesome way to build ventilated ventilation chutes, Martin Holliday had this article in GBA just using rigid foam, you know, little spacer strips, gluing those up. Very nice way to put it together, in my opinion. Also, it actually protects all of your roof sheathing rather than the inner, you know, 12 inches like those commercial, you know, rafter vent things. Because, you know, you're only ventilating part of your roof sheathing at that point. The last in one is basically trying to go for the code compliant exterior outsolation, interior insulation, but shorting the ratio of only 2 inches rather than whatever's required 40% code-wise. You know, basically, yeah, this can probably work if, you know, you keep the humidity low enough. I'm not going to make any guarantees, and the question is, how are you, you know, is your building official on the ball enough that they're going to spot this and point this out as a violation or not? I don't know. Is this, you know, safe enough? Maybe, maybe not. And this shows, oh yeah, just as the backstory, by the way, if you go to the building code 806.5, this is the table that you see where it says the minimum amount of R value that needs to go on the outside of your assembly. Joe originally wanted to write the code saying this is the ratio, and the folks who write the code saying like, no, they can't, we can't provide a ratio, we just have to put a number in a table. It's like, really? That's like, that's not, you realize that's not how physics works. If you try to do this with, you know, with a super insulated roof, it's gonna fail, but that's the takeaway. So if you know, there's one of Joe's articles, he actually states all of those ratios explicitly. That's what he originally wanted to put in the code. And that is, oh, that got through that deck, I guess.
Kohta, can you go back to that ratio table?
Yeah. Come on.
Andy, do you have questions?
No, I mean, also with that option 4, the last one we looked at, yeah, that was the primary concern, is that we're running up against and probably breaking that ratio rule. So one of the things, you know, the extra R value, it's counterintuitive because you're putting the continuous on the outboard side to get the extra R value, but then you pull back on the inside in order to make the ratio work. So I think that we were trying to explore a little bit, and yeah, you outlined exactly what I think the challenges of that are.
Yeah, the completely goofy teaching analogy I have for, you know, this ratio rule is, you know, if you're taking a puppy home from the pound in the middle of the winter, where do you put the puppy when you want to keep it warm walking through the parking lot? You put it inside your jacket, right? So you put the puppy on the warm side of the insulation, not on the cold side of the insulation. That's what we're doing here, warm side of the insulation, you know, so you're trying to keep the sheathing warmer, that's why it's inboard. The more insulation you're putting inboard of your sheathing, the colder your sheathing is gonna get. Like if you had 2 jackets on and you put the puppy between the 2 jackets, it's gonna be halfway between inside temperature and your body temperature, right?
So Kohta, what would you do with this roof? So given all these variables.
Yeah.
What would,
Yeah.
We have 14 to 18 inches on this lower roof and 18 inches on the upper roof, and we're thinking about, 14 on the upper, 18 inches on the lower. What we're trying to play around with variations, and we're thinking what different ones we would build.
Yeah. So question 0 is, what flexibility do you have going out versus in? You know, what are the constraints that historic or neighborhood or whatever?
Keep the gable end profiles the same.
But can you fatten the roof and hide it or not?
That's where the 14, you know, so like we have 2x12 rafters, so that mock-up over there on the left,
yeah,
we're showing what if we thickened the roof with, you know, rock wool or wood fiber strips. What if we thickened and thermally broke it? So the question on this assembly over here was, if we have drying potential, if we do so let's just say this is our baseline 2x12, okay? And if this is a vapor open roof sheathing, And we have a vapor diffusion port. So we use the Delta Fox, the one you showed. That's the
Yeah.
Delta Fox stuff that we use. And we put, Steve Basic was talking about this, was like one of these screenings. If we have diffusion that can dry through here, and diffusion at the top, and we do vapor control here, and we maintain the relative humidity, how risky is it? Have we mitigated it enough, or is it doesn't meet the code, but doesn't mitigate, have we mitigated the risk? That's the question.
Yeah, if you know, it's all about controlling the humidity and making sure it stays that way for the life of things. You know, I would bet it would work. I would probably cut a diffusion port at the ridge, just like I said, you know, moisture concentrates up there. Just to kick out an option though, if we're space constrained, that Salinger roof from Fine Home Building, you know, that's.
So we would take this, we would run our fabric over the rafter.
Yeah.
So we'd put like Intello over the rafter or Mento over the rafter.
Yeah, something vapor open, but shedding water.
Could we go back to that slide so you showed that roof? So has anybody done this? I've never. Okay. We'll have to start asking around. I think Jesper Cruz did this up in Maine, in Passivos, Maine. I think he did something like this.
Come on. Come on. Uh-oh. Uh-oh. Thanks. Come on. Yeah. I don't know if you quite. Come on.
So we're gonna put fabric right over the top of the rafter, dense pack the rafter, put strapping on top of the rafter, then our sheathing. Vapor open sheathing? Or
doesn't matter.
Doesn't matter at that point.
Because basically that sheathing has complete unfettered drying to its underside. And just think about it, the majority of the time, the sun's gonna be blasting the crap out of your dorm shingles. Moisture is just gonna be getting blasted out of your sheathing into that airspace.
Okay, so we trade the 3/8 on top for the 5/8 strapping, 3/4 strapping. You want a 3/4? Well, so here's the question: when we dense pack that, isn't that going to billow up? So do we have to put
I would do 2x strapping.
So 2x. So we put a 2x. So we get let's rotate the model so people can look at it. So if we dense pack it, it's going to billow up and it's going to billow down. So it has to be a thicker. When we dense pack that to capacity. What's that?
Generally doesn't balloon out, right?
Well, I don't know. That's a question of would you even if it was only a little bit, I'd say. Well, how much billowing would we? It's going to cut down on the airflow.
Depends on how tight the installer, stitches it and everything.
So if we do it tight as a drum, we still would probably put. You're saying put 2x to be safe.
Well, also, you know, in general, having a 2x cavity for a roof is kind of my go-to. You know, 3/4 inch works well for walls, but you know, roofs, let's give that 1.5, 2 inches is my thought.
Nick, you're gonna have a metal roof too, so you'll probably be doing a crisscross.
Well, that's what we want to talk. So that's what this mock-up was for, to think about too. Was so if we put the metal roof, you know, because so if you have to, well, do we need, if we put 2x on here, we're not going to need the strapping because you're going to have, we will still need a crisscross, yeah. So we could strap horizontally and then vertically.
I do up the slope first and then horizontal, because otherwise you're blocking the water.
Blocking that airflow. Okay.
And would you still fur out for thermal bridging on the underside?
Well, yeah, so the thermal break idea, so the idea was what we just did on another roof in Cambridge was we ripped down strips of Styco. Give me a hand, we'll rotate this. So what we did on another one was we ripped these down, not rock, we cut wood fiber strips, 2-inch strips for the thermal break, and then strapped it with 2x. But how thick are we now when we do that? So now we have to, but maybe we thin this down now because we've picked up thickness on the roof. So this, we're guided by if you look at the front end of this building, we're guided by the historic profiles on the gables. And we're trying to balance headroom, because Amy's office is going upstairs, versus performance.
How tall is Amy? I'm tall.
Yeah. All right, well that's, so other people have other variations. So these are the questions. So why? But if we go that, so what are we going to get to for an R value then? So we're at for the wood fiber? What are we getting for the 2x12? Matt, what do we get for? Because Timber HP is donating. Timber HP is donating the wood fiber.
Okay.
So what are we going to get here for this thickness? For this
That's like 3.8 per inch.
3.8,
Yeah.
Like R40, let's call it.
and we got to get to. We're trying to get to 49 to meet the code.
But you're furring it, if you're gonna keep the furring,
Yep.
then that's a deeper cavity.
Right.
With 2 inches of XPS and done.
Well, that'd be an option, right? So what if you could put, but the 2 inches isn't enough.
That'll get you R10, and you're already at R40.
But that's vapor closed on the interior.
Yes.
Yeah, so we
Put it
don't.
above your sheet.
Well, Kohta, well, it's not enough though. Then your ratio's off again. See, so this is the juggling. So the other option we're thinking.
Cases where people say we can't get that much insulation on the outside, and the only answer is closed cell plus whatever fibers fill, and then you have a really complicated roof with all the materials. So, how do you get there? It's like meandering path of bad decisions.
Yeah. Yeah. So we're trying. Well, so we're trying to mitigate the risk. So one of the questions I have for Kohta was, as we're trying to work in their carpenters courses, how do we give people the way to assess risk, and how do we say how risky it is? So if the number one thing is we control the humidity inside, which we can do because this is going to be a passive building, we've cut off the vapor at the slab, we've cut off the sources at the walls, and we can control humidity. And we've put a class 2, we've put a smart vapor retarder. That's another risk mitigation. And we created vapor open sheathing so the sheathing can dry, and a vapor diffusion port. We may not meet the code, but we have all these other risk mitigators. So I personally feel comfortable doing it that way. But would I do that for a client? Or would Woofy flag that? So Andy, are you on there?
Yeah, no, if you can hear, Andy can hear, but
Would Woofy flag that as a high growth thermal problem? So how do we know? Would Woofy flag these as an issue? Or we haven't run I don't know if Andy's run the high growth thermal analysis yet. So that's the question. If you have other assemblies, we're going to be running different assemblies. So when you come in here, we will show you different roof assemblies, and we'll have QR codes on them. So Andy, did you hear that question? Does Woofy flag any of these assemblies as moisture problems? Have you run hydrothermal on any of these?
We haven't run all of them in hydrothermal at this point.
Okay, so Andy is our CPHC. For those who haven't met Andy, CPHC. Andy is modeling and he knows Kohta. So Andy, when we run this one, so this one that we're talking about here, our question is that a concern? Yeah. Like. Yeah. So is that a concern? Yeah. Well, do people have questions for Andy? Because Andy has to put up with all our crazy ideas and be like, Andy, can you model that? Yeah. So Andy, does people want to ask Andy questions too as we're modeling these?
Can you put Andy, what are you drinking?
All right. I'll put Andy back over here so you can see. Do people have questions for Andy?
I'm being brought around.
Yeah, you're being brought around. Yeah. Questions for
The goal is R49 for this? Is that what your goal is, you said?
I don't know what our goal is.
We have to hit.
Well, we're going for passive house certification. So Andy, the question was, are we going for R49? We're going for passive house certification so we can trade assemblies total R value based on the whole envelope.
doesn't have to be.
14 times 3.7, because 3.7 R value per inch, that would be 51.8.
No.
So 12 inches plus your furred out 2 inches, that becomes your whole bay is dense packed.
Yeah.
So that's 51.8
Yeah.
R value there.
11.25, right? Yeah. For 2 and 12.
But we've just added thickness to our roof,
Yeah.
plus the thickness Kohta added for the ventilation channel.
Yeah. Well, what I'm hoping is the ventilation channel on the top side is not that crazy of a profile change. Plus, we're getting back to the
Strapping too, right?
yeah,
We're
the
getting
1 inch of the original sheathing.
Okay, so Kohta, you said this. So Steve, we looked into this product because Steve Basic mentioned it. This is called AquaGuard or entangled mesh. But Kohta said he does not consider this a ventilation channel.
Well, it's not a top side ventilation versus protecting your sheathing ventilation. That's the biggest objection.
So what would you define ventilation? So when we're playing with the thickness of the strapping and the billowing of it, so if we take the sheathing off and we tack the Mento on tight, what channel would you feel is a good, like, do we have to go? So this is that game of inches. so this is only 3/8, and that's not enough. Would you feel comfortable if we had 3/4 clear or an average of 3/4 airspace? Or do you think that that's...
It's still topside better.
No, underside. We're gonna go underside, right? Because now the sheathing is gone. The sheathing's gone, and we've pulled our material, you know, whatever it is we end up pulling. Yeah.
So you could have entangled meshes over the membrane.
Steve had said he puts this on top, and you put it under the metal roofing.
Yeah, the thing is though, I think you're running up against code because doesn't the vented cathedral roof call explicitly 1 inch minimum or 1.5?
I don't know. That's why I'm asking you.
I think it's something, you know.
Okay, so there's a minimum requirement for this channel. Okay.
Say that one more time.
Minimum requirement.
For the bench. What is it? Bench or inch and a half?
Somebody in this room must know the answer.
Do we know what section is quoted?
806 4-ish. 806.5.
But I thought soffit vents, I thought the ratio of a soffit vent to an attic space was like 1/300th of the total floor space.
1/300, 1/150 stuff. That's the net free area of low and high.
But
This is talking specifically about when they have like cathedral, you know, or you know, vent chutes, that kind of stuff. And I thought there was a requirement for a minimum dimension, but
Okay, all right. Andy, we got more models to build. So we're encouraging people to suggest other models they have questions on. And when you come into this space, we could have different QR codes to different types of models. Now, we're not going to build. So other ones, what might we else build? What else, when you're looking at this, what else might you build? So we've got the Salinger. That's a...
What would be interesting?
Yeah.
What's the other assembly you may have thought
before
of?
you jump off of that one though, the other thing to check is whether or not structural sheathing spaced off the rafter by, you know, a piece of 2x is a no problem condition, or will structural flip out?
Oh, from a shear perspective.
Exactly, shear diaphragm, all of that stuff.
Structural not.
Okay,
Only
cool.
because I've done that before and the structure, so what the structural engineer needed to do, though in my case I have topside insulation. He, for future PV install, we have to thicken up every 4 feet. We need like a thicker rib.
Okay, got
So
it.
that
There's something to bite
there's
into.
something for that to bite into.
Got it.
So, but in terms of the sheathing spanning between, that hasn't been.
Okay, fair. Yeah, so other assemblies that might be interesting. Jeez, I don't have any research ideas in my head. You know, how, you know, I guess part of it is how risky do you want to play with and that kind of thing, or. You know,
So on this lower roof, we have a low pitch roof here that goes to this upper pitch roof. And on the low pitch roof, we have like 18 inches. So like we can play with different thicknesses. So sometimes we'll get the question of like, well, what if we ran wood fiber on the inside, like continuous? So is that ever a concern? So people will say, and I don't know about this, I've never seen this done, but if somebody said, well, I want to run this continuous on the underside of my sheathing, do you worry about that?
Well, it's vapor open, so there's nothing that I really object to. It's basically self-supporting insulation. It's nothing fundamentally different from like another cross-strapping cavity with bats, for instance, right?
So you don't view this as doing anything different because it's not like foam where you're going to trap it. So this can breathe through.
Exactly, it's fully vapor open.
What other questions people have about assemblies? I feel like we keep drawing up various ones, and I'm trying to think of other variations on this that we could, you know, we want the thermal break, we want the drying potential.
Yeah, in terms of thermal, there's no reason to build it, I would say. Frankly, doing, you know, just a basic spreadsheet calc, or if you want to be fancy, do a therm model or something, and, you know, there's no need to build stuff in order to figure out how it's going to perform thermally. You know, it's a known solution. Yeah, like if you wanted to build this one, which I considered a bit risky, as, you know, a side-by-side comparison with the Salinger roof, that, you know, and monitor the snot out.
So what would you monitor? You would monitor you'd monitor the relative humidity of the sheathing and then the cavity itself. Would you do both?
Moisture content of the sheathing, low, mid, and high, north and south. So north is always going to be more risky than south because it's getting a lot less solar. and the high portion is where the moisture all concentrates into. You know, if you look at the data from that, 120 pages of graphs and crap, you'll see that if you're looking at the lower readings of moisture contents on the roofs, like they're all fine. It's just at the ridge where we're having risks. So my dumb conclusion was, if you're going to build a risky roof, only build the lower half, and you're all set.
Okay, so if we're gonna put sensors, that's helpful too, because Ben Bogey offered to put some sensors in and like monitor. He's like, I'll supply the sensors and monitor. Yeah, Matt, you got one?
Nick, I'd be curious about different densities. I know that I've done this a few times, and it's tricky, but what does that assembly look like when timber fill is installed at 3.5, 4 pounds per cubic foot versus 3,
So-
which clearly would settle, and then that goes to your point that you saw this cellulose settling, which is not a good thing, but what real effect is that?
Okay, yeah, so part of this idea was that this is going to be accessible because people will always be coming and going. So this wall is going to be tools, and like our models might roll over here, but when you come in, like assemblies, this is easy to access and we could take it apart.
Right.
So maybe we do dense pack and we do density. So maybe you'll come down and set the densities you want, and then we'll put the sensors low, medium, high, and then and then maybe we create some plexiglass look-ins from above where you can see if it's settling too, right? Maybe there's room upstairs where we could look into and see,
Yeah. That's a good idea.
Although plexi is vapor closed, if that makes a difference to you. But,
Well, just so we can see into the assembly without taking it apart like an ant farm.
yeah. That's not the part.
Are there things you could do with the densities? Like in the test cut, it looked like it was maybe a 12 to 14 foot span.
Yep, ish, yeah.
Dense packs in there, 12 inches deep or whatever.
Yeah, I think
Maybe
it
it's a
was
2x10 or-
14. It was basically a 2x12 with a 2x4 stacked on top.
Okay, so it's real deep.
Yeah.
Could you take that and, like I've heard, like every 6 feet, make a section basically?
Sure.
What if you made that smaller? What if you made sections that were 2 feet deep, like 2 feet, 2 feet, 2
Right.
feet, and did
You segment it into different densities separated by insulab.
Or I'm saying like
something.
even like say you did a whole bay at 3 pounds per cubic foot,
Yeah.
but the bay, the chunks that
Gotcha.
were isolated from each other were smaller.
That's an art, not a science.
Yeah, I'd suggest if you're doing experiments, do
Yeah.
rafter bay by rafter bay
Right.
experiments.
Well, no, I'm saying that. So the whole bay is going to be 3 cubic
Okay,
foot.
just making sure you're talking about dividing stuff up.
Yeah, but
sure.
no, but I'm saying like you're sectioning off different sections of it so that you don't have one big mass insulated to 3 pounds per cubic foot. You have a little bit and a little bit and a little bit, so it's not the whole thing weighing down on itself. It's like you have a little.
Blocking as you go up the rafter.
Yeah.
You're speaking to the idea of like a consistent density across the entire rafter
Yeah.
bay, and by chunking it out.
So it
you
doesn't
have
settle,
more
may not
control.
settle as
Oh,
much
you're
because there's
separating.
less mass.
Yeah, basically compartmentalize. I do that with netting or something. Isn't that
Right,
common?
like an insulab
Yeah,
or something.
yeah,
Yeah.
Amy's going to be trying to work, and we're like, we're turning up the humidity to 90%. It's going to be a jungle. We're like, Amy, don't try to work. Yeah. Yeah, okay.
There we go.
Yeah, it's going to get a little hot and humid. Yeah, we're just running a few experiments.
By the way, are there any skylights planned or not?
Yes, we just
Okay.
got historic approval for 3 skylights on the north
Okay,
side.
which makes the office far more livable, but
Yeah.
a lot of the the conventional vented assemblies are far harder if you're doing skylights, because those are interruptions in your ventilation. If we're doing this Salinger roof with the membrane, we can like short the 2x and provide a pathway around the skylight.
Oh, we can diagonal the strapping to allow
I
airflow.
thought it's just like put a gap in the
Basically
strapping.
like a inch gap
Yeah.
before it hits that skylight, so air can come. So say the skylight can come up, instead of hitting into the skylight, you hold that piece of that 2x furring strip or whatever we're calling it, sleeper,
instead of dying it right into the skylight, you just leave it back a little bit. So air can come up.
Okay, so I got a question here. So I'm a little surprised. So if the vapor, so this is what I'm trying to get my head around. So if this, so this is the Delta Fox that we saw Joe's presentation on vapor diffusion ports. We started using it on our thick roofs as a safety precaution. So we started using the Delta Fox vapor open airtight, taping it along the ridge. We cut holes in our sheathing, and then we like ran it down our ridges on our thick unvented roofs for a safety precaution. So, but my question for you is, so if we have this, I don't know what the perm rating is on this.
300.
300. So, okay, so so we have this really high perm rating, and then we've cut the holes in the sheathing with a 3-inch hole saw to allow, like, it doesn't have to go through the OSB because the OSB is the low perm rating. So, if we put something like this though on the entire roof assembly underneath, over the CDX, you're still worried about the underside of that sheathing getting wet and not drying through it?
You're not putting the holes anymore.
Yeah, but the CDX, what's the perm rating on the CDX?
It's wet cup, dry cup varies a lot. So, by the time it gets wet, it opens up pretty well. Is that enough? Maybe. That the previous, this iteration that you built here with just the mesh, am I saying, oh my God, it's going to fail? No. I'm saying like,
we don't know.
It could work, but is it code compliant? Nope.
Yeah. So we're off the map. But I think a lot of the stuff is we're off the map. We're trying to navigate outside of the.
Yeah.
So this is 300 perms. Wow, I didn't even look at this. I just saw you guys were using it and we just bought it. I didn't look at the perm rating.
You might already have a lifetime supply, but Delta has stopped selling Fox in the US, but Delta Facade is the same product essentially.
Delta Facade.
But it's black.
Wow. Okay. What else, any other people? We're gonna have. I think this is a lot of information. We've got a lot of assemblies, and we're glad to have Rope Kohta to come in here. And I think when people want to, we have to be out of here by 8:30. How are we doing on time?
It's 5:08.
So if people want to hang out, we can wrap and we can ask Kohta to come back maybe another time once we get a little further along. Would you be willing to come back maybe and look at all our crazy mock-ups if we? Yeah.
Can I ask you a quick question?
Yeah.
So this came back to the point you were making about relative humidity.
Yeah.
And you were talking about all the things that are not the occupants.
Yeah.
How much have you found that the occupants versus the actual envelope and allowing vapor to enter through moisture? What's the ratio of that from if you do vapor barriers on your slab and good walls and good ceiling, how much of the humidity is being created by the occupants' activities themselves versus moisture coming into the building? Because they're the same thing once they're created, right?
Yeah, so just to clarify one point, just to make sure people aren't walking away with the wrong thing. I'm only talking about wintertime humidity as the risk factor, to be clear. So, if you're running 60% relative humidity in the summer, I don't care. You'll be uncomfortable, but I don't care. But in the winter, that's, high humidities are what causes that problem. To me, if you're talking about modern construction, the shell versus how it's driven, I would say that the shell is a pretty small component.
So it's more the occupant behavior that you got to kind of make sure that people understand.
The occupant behavior and the ventilation system, the air change. Air change in winter in New England will always pull humidity down. Full stop.
And if you don't have it, you'll be at least 50% humidity based on my own experience.
And the air tightness. So like the inadvertent experiment that I had was working with Carter Scott Transformations in Devens, Massachusetts. He was building all these double stud houses. We were monitoring them. He's doing low cost stuff, so his ventilation system was just a bathroom exhaust fan running 24/7. I looked at the first year of data and I'm going like, why is the humidity so high? It's like 45, 50% most of the winter, and it's family of 4 doing normal family things. And the electrician wired up the exhaust fan to be just on the wall switch, not running 24/7. Guess what? They didn't have a ventilation system in a under 1 ACH 50 house. Wow. So that's what you get.
That is what you get.
Yeah.
I have a question about my house for you.
Yeah.
Which runs at 50% humidity all winter long in the URV. So I've got 2 by 10, 2 by 12, 2 by 8 rafters that will be dense packed or filled with batt, with fiber. On the outside, I have from 4 to 6 inches, depending on the roof, of recycled polyiso
Nice.
with 1.5 inch sleepers and then a nail-based sheathing on the outside, so it's vented.
Cool.
And at the ridge, I have a diffusion port, which is Sega My Vest over the ridge, about that wide, and then that void is filled with rock wool.
Okay. Yeah, that sounds like as long as you're hitting the 40% outside, 60%, you're good to go.
So here's my question though. Do I need a smart vapor retarder, or is drywall with latex paint enough?
The way the code was intended to be written and is not explicitly in there, painted drywall should be fine. But one slight tweak on your diffusion port, I would probably steal some stuff from Nick, the brown stuff, rather than using My Vest. My Vest is
not open enough.
Yeah, I think it's like 3 tons wet cup, or it's like not
way past the point of being able to do that. But I was. What was I just say? Yeah, I was thinking of the diffusion port. I'm like, I'm there. It costs $150 for the roll. Why don't I just put that in?
Okay.
It doesn't add. I mean, without that, I'm still code compliant based on everything we learned.
Oh yeah.
Okay. I was just like, I'm here. I'll put this in. It's like a little bit of safety factor.
Yep.
But next time I'll use the brown stuff.
Okay. I'll do.
It's black stuff now, he said.
Clarity, so the, that diffusion port,
Yeah.
is there any, if I just leave a gap in, like, between this sheathing that comes up and that sheathing that comes up, why do I need to cover it with it?
Because.
But if it's entirely outside of my installation?
Let me just make sure we are talking about the same thing. Just yeah. So yeah, building and water. Exactly. That's what I'm worried about.
But what if if I'm using like XPS or polyiso on top, and that's a fully taped.
Oh, sorry. We're talking about
topside
insulation.
Topside insulation.
Yeah.
With a 2x on flat as my ventilation battens.
So, structure, exterior insulation, battens, topside sheething.
Correct.
At that point, I just do a vent, not a diffusion
Okay,
vent.
yeah, that was the clarity I was.
Okay, cool.
Thank
Yeah.
you. Yes. Okay.
Yeah, if you have the intent of this is just we have a closed, insulated cavity that we're trying to let moisture out.
But so I guess with the idea that you guys are talking about, if you do that, that assembly that has the mento on the top side, the rafters,
give a quick
and
roundup
then
was
those sleepers.
Yeah,
Interesting.
the Salinger roof.
The Salinger roof, and what is the detail at the ridge in that case? Is it just the mento going right way across?
Let me see where did that presentation go?
Good.
Yeah, so up at the ridge is
Yeah.
just ridge, it's an open air cavity.
Just an open air cavity.
Yeah,
Okay, so-
let the air out.
Yeah.
Don't need you need a diffusion port in that.
It's not needed.
Okay, got it.
Correct. Yeah. So I think people should feel free to.
All right, thank you, Kohta.